July. So in the last class we ended at law of diminishing marginal productivity and law of variable proportion. So I am beginning from that only. So again, as a brief recap, the first is your law of diminishing marginal productivity of labor, or it could be any other factor. I'm simply writing MP. And I also stated that the reason behind this law is, if you have an like the reason is that there is law of variable proportion. What does this law state is that as you increase the employment of variable factor, keeping other factor constant, marginal productivity will eventually diminish. Here I am using this curve. What is this curve? This curve is the curve of MP, which is marginal productivity of a factor 1. Now what it states is that eventually, as you keep on increasing the employment of the factor 1, your marginal productivity, additional productivity of that factor will initially increase. Say here from point origin to D, it is increasing, but after some point it will eventually diminish. So the shape of marginal productivity curve will be like inverted U shape. Again, the reason behind this is law of variable proportion. As I said, that as you keep on employing more labor, initially there will be better coordination with respect to your fixed factor. Initially there will be better coordination. You might be having specialization and divisibility of labor. So your factor ratio, what is factor ratio? Factor ratio is the ratio between two factors that you are employing. For instance, say I am using K represents your capital. Say capital might be a machine. So you have might be fixed throughout you are not changing this. And the second is your L. L stands for your variable factor. In this case, it's labor. So labor, you are increasing the size of labor. Then factor proportion is this K by L ratio. This is your factor proportion. Say here it is 1:1, then it's 1/2, then it's 1/3, then it's 1/4, then it's 1/5, and that it's 1/6. So this is your K by L ratio is your factor proportion. Initially, as you keep on increasing the employment of your variable factor, your factor proportion will be conductive to some extent. But after that point, say this is your optimal point where you will be having highest productivity. Your marginal productivity be highest. Say over here it's point D. If you keep on employing again, then your variable factor will be overcrowded. Since you have limited amount of, you have only one machine, but now you have a substantial amount of labor, large amount of labor. So the addition of the marginal labor will keep on decreasing, and eventually it will diminish. So that is what the law of diminishing marginal productivity of labor represents. So whenever you have such kind of question, whenever there is an explanation to law of diminishing marginal productivity of labor, you can also use the case of law of variable proportion, because both the two are related, and you can use this particular inverted U-shaped MP curve to explain it. So the next subtopic is stages of production. Or you can also say that it is shapes of TP, which is your total product, MP, marginal product, and average product curves. So this graph represents the shape of curves. This is your total productivity curve. So here in the next one I have drawn average productivity or AP curve and marginal product curve. Now this question is again related to stages of production. Now generally in production, especially when you have a fixed factor, so in such a scenario other factors are fixed, only factor 1 is changing. So you might be having 3 stages of production. Now here from this point to this point, it is your stage 1. And then from this point to this point, it's stage 2, and beyond this, it's stage 3. I'm writing here what are the properties of stage 1 and stage 2 and finally stage 3. This point is stage first, sorry. So in the stage first, your total product is increasing at increasing rate. So it is increasing, sorry, up till point F, it is increasing at increasing rate. And after F, it is again increasing. Now it is increasing at diminishing rate. So this point F is called point of inflection. That's the point. Beyond F, it is now increasing, but the rate is diminished. Up till F, it is increasing at increasing rate. So as a whole, over here, TP is increasing. Sorry, this is it's increasing. Now initially it is increasing at increasing rate, then it is decreasing. It is increasing but at diminishing rate. Second is, now if we look at MP, that is MP curve is here increasing, and it is reaching its maximum possible point at D, which corresponds to your point of inflection F, and after that it is decreasing. So in the stage 1 itself, your MP is increasing, but beyond point D, it starts decreasing. So that is the trend of MP. So MP is initially increasing, and then decreases. Now the third is, what is the shape of AP? Again, AP itself, because what is your average product as a whole? If I write it here, AP is simply average of your summation of marginal products by X1. So it being the average, it is also following the same pattern, but the magnitude might be much lower than MP. That means it is also increasing. MP is also increasing, but MP after some point it starts decreasing, but your AP is increasing. So as a whole, in the stage first, your AP reached up to its maximum point. So AP increases and reaches its maximum value. So this is your stage first. Now beyond that, you have stage second. Now what is the, in stage second also your total productivity is increasing and it is reaching point H, which is its maximum possible value. So here also TP is increasing but at diminishing rate and attains its maximum possible value. So TP becomes maximum at the end of stage. At the end of stage 2. Now as far as MP is concerned, your marginal productivity curve is now completely decreasing. From point S up to this point, it is decreasing, and its MP decreases and attains zero value at end of stage 2. Here you are saying from S it keeps on decreasing and eventually it becomes 0. This is your horizontal axis, the value is 0, so it attains 0 value. Now as far as average productivity curve is concerned, so this is point S is also the point where AP reaches its maximum. From point S onwards it starts decreasing. So in the stage second 2, initially AP is at its maximum possible value, and after that it starts decreasing. So AP starts decreasing after attaining its maximum value. AP attains its maximum value at the end of stage 1. Now what is the stage third? That is the third stage. In the stage third, already now your total production is at its peak. So beyond it, now it starts decreases. It starts decreasing, or you can say TP starts decreasing. As far as MP is concerned, now in this stage MP is negative. That means the marginal productivity of an additional labor will be 0. For instance, say there is 5 labor. I am employing 5 labor and the productivity is 100. And after that I am employing the additional labor, 6 labor. Again your productivity is not 100 but say it's 98. Then what will be the marginal contribution of this last unit of labor? It's -2. So that's like we are in stage 3. So in stage 3 your MP becomes negative. Now as far as AP is concerned, AP will decrease but it won't be negative. So AP is decreasing. Again here AP is decreasing. Now the question is, as a producer, where shall he produce? In which stage? Shall it be stage 1, stage 2 or stage 3? Now here what we say, in stage 1 your marginal productivity is increasing. So a rational producer will still like to produce more and more because still your additional labor is giving some kind of contribution. So he won't be producing in this particular stage, or you can say this stage will be, he will reject this particular stage. Similarly, if I come to the stage 3, again in stage 3 you are having this particular labor is having negative productivity, his marginal productivity is negative. So he is not producing in that particular stage. So a rational producer will eventually produce in stage 2. So the next topic will be about long run production function. Again, at a higher level, we studied that laws determining production, or you can say laws of production, will be different for different time period. Say one is return to factor, which we studied till now, and then there is a new concept called return to scale, which we will be doing. return to factor determines your short run production function. Short run production function. Now what is this short run production function? We know that in short run production function, some variables or some factors are fixed. And only one factor is variable. In the earlier cases, we studied that your labor is flexible and capital is fixed, which is the classic case of short run production function. Over here, your factor proportion. Factor proportion is K by L ratio is changing. That's what we studied till now. Now, return to scale will be applicable to long run production function. If in production function, in the long run, a particular producer can increase or decrease the size or quantity of all factors. That means both your labor and capital or any other factors can be changed easily. So here all factors are variable, both x1 or x2 in a 2-dimension, or it could be any other factors, all are variable. So here your factor proportion means K by L ratio or anything is constant. To understand it graphically, okay, we can use the help of isoquants to understand it in much detail. On vertical axis you have factor 2 and here you have factor 1. Now what are isoquants? They are different combinations of factor inputs that give you same level of output. So I am drawing some isoquant. So that is Q0 and that is Q1, and say this is your Q2. Corresponding to this, in the short run, what is the thing is that your factor 2 is constant. The only way you can increase your production is by employing more and more of factor 1. Or in other words, say this is the factor 2. Your factor 2 is constant. So I'm putting a ceiling. Factor 2 is constant. Now in the short run, you can increase your production, say from point A to point B which is Q1 to point C only by following this path, which is also known as production transformation path, because you have some kind of limitations or constraint. But over the long run, you can follow this path also. In the long run, since you are not now, you don't have any kind of ceiling, so you can increase your production by employing more of factor 2 also. So this is something which will be governed by return to scale, it is by return to factor. Here you are following this path A, B, C, while here you can follow from point P, you can jump to point Q, and from Q you can jump to point R, and so on and so forth. That will be the difference. I hope you understand it clearly. In the short run you have ceiling, in the long run you don't have any such constant. Now again I am coming to this curve. As far as return to scales are concerned, it will be also of three types. First will be your constant return to scale, second is your increasing return to scale, and the third one is your decreasing return to scale. Now what does, in plain English, constant return to scale represents that if you increase the proportion of your input, your output will also increase by same proportion. Or say if I increase my inputs from 1 to 2, your output will also doubles. That means it will move on a proportional basis. Under increasing return to scale, if I double my input, my output will increase by much larger times. Say so initially your input x1 be 2, x2 be 2, and your output is 10. Now you have increased from x1 to 4 and x2 to 4. But that means both your inputs are doubled, but your output will be say 50. So that will be the case of your increasing return to scale. The last is decreasing return to scale. Under decreasing return to scale, if you double your input, your output will increase, but it will be increased by much lesser amount. Intensity will be much lesser. Again, say I will rub it for a while and try to show what does it means from this particular curve also. Say initially you are at point P, you are producing at point P. At point P you are employing 1 unit of factor 1 and 1 unit of factor 2. Now from point P you have increased your scale and you reach point Q. At point Q, say it is 2 factor 1, and say this is factor 2 is also 2. So you have doubled your factor input. Now say initially say your Q is equal to 10, and now input is say 20. Doubles. Your input has doubled, your output has doubled. Then in such a case we call it as a constant return to scale. Now in place of Q1, in place of 20, say the value is now 30. So sorry, 30. Now what has happened? Output has increased by a larger intensity. So in such a scenario we can say it is your increasing return to scale. Now say the third scenario. In such a case, say your output is now 15. Now output has increased but the scale is much lesser. So in such a scenario we use the term DRS. DRS represents your decreasing return to scale. Okay, we can use this to understand it in a much detail. This is a simple production function. Now this represents your long run production function because there is no bar on x2, which means your output is a function of both x1 and x2. Now in case of constant return to scale, what I have done is that in place of x1 and x2, now I have increased it by certain multiple. Say the multiple is t. So your input has increased by tx1 and output has increased by tx2. And if the total output has increased by same intensity, here intensity is t, then it represents your constant return to scale. In the second case, now you have doubled your input but the intensity is much larger. So this represents your increasing return to scale, your output. and this represents your decreasing return to scale in the same manner. Example is again in the book, in your NCERT book, your Cobb-Douglas function is given. Again, we have different kind of production function. We have log linear production function, we have linear production function, and this is the case of Cobb-Douglas production function, whereby your Q is simply x1 power alpha, x2 power beta. Alpha and beta are simply constants. Now suppose say if your x1 is x bar and x2 is x bar, x2 is x2 bar, then the value of Q naught, original output, will be x1 bar, x2 bar. Now suppose again like this, if I have increased my inputs by multiple of t, by t times, then what will be your total output? Your Q1 will be t alpha plus beta x1 bar, x2 bar. I can solve it also like using this. Initially your Q naught was here x1 alpha, x2 beta. Now I'm increasing both the value of x1 and x2 by t times, so you are having a Q1. Now Q1 will be t x1 alpha, t x2 beta. Since both t and tb also have the same powers, when you have same value but different powers, you can easily add it. So I'm just bringing it away outside, t alpha plus beta, and within the bracket you have x1 alpha, x2 beta. Now in such a case, if the value of alpha plus beta is 1, as seen here, we will be having constant return to scale. If the value of alpha plus beta is larger than 1, then you will be having increasing return to scale. And if the value of alpha plus beta is less than 1, then you have decreasing return to scale. As far as these economies of scale are concerned, generally it could be due to internal reasons or due to external reasons. We call it internal economies or external economies. External will be when you will be industry specific. When you have a larger industry, you can easily delegate work to different you don't need to produce all the raw materials yourself. So you are so that will be the case. In industry firm specific, you might be having different kind of departments and other kind of like